So we left off on alkene hydrations. So there's actually three types. We looked at acid catalyzed hydration. We looked at hydroboration oxidation, was the anti-Markovnikov style. And what we're going to look at today is oxymercuration demercuration, or we're going to continue with oxymercuration demercuration. Oxymercuration demercuration uses mercury acetate, water, and THF. THF is tetrahydrofuran. It's a solvent. Now this is a two-step reaction. You never do the first step without the second, but it's two processes. You add the first set of reagents, then you add the second set of reagents. Second set of reagents is sodium borohydride and base. Okay, and this gives us an alcohol. Now, reason we'd use oxymercuration demercuration is that if we had done the same reaction in water and acid, we would have ended up with the major product from a 1,2 hydride shift. Okay, so this goes through a carbocation and we can get a hydride shift. Yes, ma'am. Mm-hmm. Oh, AC. So it's acetate and then there's two of those. So there's parentheses around them. Right. So why we would use oxymercuration demercuration is when we have a substrate that could do a carbocation shift, either a 1,2 hydride or a 1,2 methyl shift, and we don't want that hydride or methyl shift to occur. So the oxymercuration demercuration gives us the same Markovnikov style alcohol without rearrangement. The way that works is that the nucleophile reacts with the mercury. So the alkene is nucleophilic, the mercury is partially positive, so it is electrophilic, so nucleophile attacks electrophile. Now a little bit different here, we have the mercury also then attacking the other carbon, right, the more electrophilic carbon, and with loss of a leaving group. Okay? This all occurs simultaneously. You can also, you will sometimes see this where the mercury has disassociated. So if you go and look at other mechanisms, it'll show the mercury in this formation. That also is acceptable. The concept here is that the mercury is both being attacked by the nucleophile, the alkene, and also then making another bond with the nucleophile, with the alkene at the same time. So what that does is leave us with the species. Because of this cyclic intermediate, we don't get any rearrangement, right? We don't have a full carbocation here, so we're not going to get hyperconjugation between the adjacent groups. We're not going to get any 1,2 or 1,2 hydride or 1,2 methyl shifts. How we get the product is then the water that's in the first reaction actually comes in and reacts with this. Now it's got two places to potentially react. Okay, it's got the primary position and the secondary position. If we're thinking about those two positions, which position is going to have more partial positive character? Well, the position that could withstand more partial positive character, right? So if we're thinking about a primary versus secondary, which one of those two is going to be partially positive? The secondary, right? So the more electrophilic position is the secondary position. So now we've added our alcohol. Then we'll have another water to do a proton transfer. So lone pair picks up proton, electrons go back to the oxygen. I still have my mercury attached. But now I have my OH in the Markovnikov position. Then the last step, we're not going to show the mechanism. The mechanism is still somewhat disputed. So we put sodium borohydride in base. That sodium borohydride replaces the mercury. So that's the demercuration process. Questions about oxymercuration, demercuration? So we have three ways to make alcohols. Let's look at a few examples of where we might use each of those. So we're starting with the same substrate here. Okay. So before we can pick the reagent, we need to analyze our product. So if we look at the first one, we've got two possible positions across the alkene, and that's one thing to think about, is that normally you're adding across the double bond unless a carbocation occurs. So if we look at that, we've added to the primary position over the secondary position. Since we've added to the least substituted position, this would be an anti-Markovnikov style product. Okay. In the second one, we've changed our carbon skeleton. Okay, so we've changed the carbon structure. And then the bottom one, we've got our, standard Markovnikov alcohol, right? We've added to the secondary position. no structure change. Okay. So in the first one, anti-Markovnikov, well, that's going to be hydroboration oxidation. Okay, so first step is borane in a THF solution, followed by hydrogen peroxide in a basic solution. That'll give me anti-Markovnikovs. The second one, I have to form a carbocation, which three of the possible hydrations forms an carbocation. So the acid catalyzed reaction forms a carbocation. So water and H2SO4. And then the last one, we have standard Markovnikov, no carbocation change. Now we notice that we have a tertiary group, right? So if we form a carbocation, we're going to get that to rearrange, right? Because we have a quaternary group next to a secondary carbocation. So therefore, if we want to add the alcohol without structural change, we're going to have to use our oxymercuration, demercuration. So we add our mercury acetate in water, followed by the second step, sodium borohydride and base. Okay, so whenever you have more than one way to do things, as we go through, this will happen several times, you need to think about how do I determine which one I need. And often that is by analyzing your product, right? Okay. A little warm in here, right? All right, questions about oxymercuration, demercuration? Next reaction, halogenation. So we're going to do halogenation. We end up with the two bromines added across the double bond. And notice they are in, one is above and one is below, right? This is called an anti-addition. Okay, we're adding one of the bromines to each face of the ring. Okay, so we're going to have stereo control here, and the stereo control is anti-addition. When we look at the mechanism is somewhat similar to what we saw with the mercury. So we have the nucleophile attacking the electrophile. Why is the bromine electrophilic? This is an instantaneous dipole situation. Bromine is very electronegative. The other bromine is very electronegative. If you have two kids that really want a toy at the same time, what do you get? One kid has a toy, the other kid has a toy, the other kid has a toy, go back and forth, back and forth, back and forth. You're always going to have something that has more toy than the other. Same thing here. You've got two elements that really want that electronegativity. So you end up with the bromines always ending up being partially negative, partially positive. So the bromine here has an instantaneous dipole. Right, so we end up with a partially positive. Now, like with the mercury acetate, you get two things occurring at the same time. You get the bromine going out and the alkene reacting with the bromine with the other bromide leaving, but you also have the lone pair of the bromine coming back and reacting with the alkene. So if you notice, this looks similar to the mercury, and we'll see this one more time today. Right, so this is a concerted mechanism. And now this first bromine could have added to the top or the bottom, but I'm going to add it to the top. We end up with that Br plus, similar to the mercury. At this point, the bromine comes in to ring open this, and it has to come from the bottom side or back side. Because to ring open this, just like with an SN2, it's got to come in at the anti-bonding orbital. That ends up giving me the anti-addition of the bromides. So walking through that again, the nucleophile attacks the electrophilic bromine, kicks off the bromide, and then the lone pair from the bromine comes back and attacks the alkene, forming the three-membered ring with the brominium. So this is a brominium ion. So brominium ion, then the bromide comes in, attacks, ring opens that, and we end up with the dibromide in an anti-addition formation. Questions about this one? Chloride tends to do this, and iodide does do anti-addition. So chlorine tends to do anti-addition, bromide always does anti-addition, and iodine always does anti-addition. So when you're looking at the different halogens, you'll notice that he used bromide most often because bromide is one of the easier ones to work with. Iodide is not that difficult to work with, but bromide reacts a little bit faster. So you notice that we use the bromide more often. Now we can have some possible changes to this, and that is a halohydrin formation. At first glance, the halohydrin conditions seem very similar, except for the solvent. Okay. So here we have water as our solvent, and so we end up with a halohydrin, halo being the halide, and then hydrin, water. So we have the halohydrin. Now, if we notice up here, I put the CH2Cl2 underneath, but the CH2Cl2 does not play part in the reaction. Usually when you see something like CH2Cl2 or CHCl3, those are solvents that are very easy to make dry. That means dry, not meaning the solvent is not liquid, but dry meaning there is no water, okay? So whenever you see this in a reagent, it's usually indicating that you want to run this reaction without water. And that's what's happening here. This is not part of the reactant. It's not necessary. I could change my solvent, but any solvent that I want to use, I need to make sure that that solvent doesn't have water. If it has water, then the halohydrin is a possibility. So if I want to do this reaction, what I can do is just make sure there's plenty of water around. Now, this might be water and ethanol. You'll see that often. Water and methanol, you see that too. Water and DMF. But if you see a halide with water shown, right, then what you're getting is a halohydrin versus the dihalide. Now, how does this work? Well, it's similar to the previous mechanism. It's just the second step. We have a different nucleophile. So nucleophile attacks bromide. Electrophile comes back. Now we have the Br, but we also have water. Now, which of these two are we going to have in higher concentration? How much bromide? Bromide are we going to have at any one time? Well, the bromide is only going to be the amount of bromine that has left, right? So if we think about this, we're only going to be creating the bromide when this process occurs here. How much water do we have? Well, as much water as we have in the solution, right? And if it's only in water, if we did this reaction only in water, then we have lots and lots, right? In fact, both of these molecules are surrounded by water. So if we think about concentration, right, water is going to be in a higher concentration than our bromide. Bromide will always be in a small amount of concentration because it's only being produced as the reaction starts to occur. So water is going to be in a higher concentration, and that's really the reason that this reacts with water. Is just a concentration effect. So the water comes in, attacks the bromide. We add the water to that reaction, and we need a proton transfer to finish it. So we'll add more water. We've got plenty of water. So that picks up the proton. Electrons go back to the oxygen. Okay, questions about this one? So again, we get anti-addition. We can also here have regioselectivity. Here we've added the OH to the more substituted side. If we think about the mechanism, nucleophile reacts with the bromine. Bromine comes back and reacts with the carbon. We end up with bromine. If we look at this one, we can think about if we had that partially, that one of those two sides partially broken, which of those two sides would be more stable? Okay, so if we think about that not being totally secure, but we start to stretch one of those two bonds that makes the brominium ion, which one of these two the partially positive carbons is actually more stable? The secondary or the tertiary? Which one would be more stable if it's a carbocation? Tertiary, right? So this is more stable. So if we think about this structure, there's going to be a partial amount of this structure there, which means that we don't have equal electrophilicity in our two carbons. That means that whenever we come in and react with the water, where is the water more likely to react at? The water is more likely to react at the more substituted position. Of course, we get inversion at that position. The stereochemistry is still the same, but the regional selectivity is that the OH attacks to the more substitute side, or the second addition, right? The water attack occurs at the Markovnikov position. Okay. So dihydroxylation, we've got two possible stereoselective processes, and I haven't pointed out yet, but whenever we show one stereoisomer, you also would get the enantiomer. I haven't shown you any enantioselective reaction, just stereoselective anti or additions. Okay. So we could add two. Dihydroxylation means we're going to add two alcohols, so two OH groups. We could end up with an anti, or we can end up with a syn. Anti-addition starts with epoxidation. So anti-dihydroxylation is a two-step process. Starts with epoxidation. An epoxide is a three-membered oxygen ring. What we need to do is reaction of peroxy acid. The ones that you're going to see, you'll see CH3CO3H. You'll see something called MCPBA, and the P stands for peroxy benzoic acid. You may also see something like CF3CO3H. What you're looking for is something that has this structure. Okay. Or a peroxy acid is, it's got one extra oxygen. So think carboxylic acid with an extra oxygen. The mechanism on this one is kind of like the bromide and the mercury. We're going to have several things happening at the same time. This one gets a little bit more convoluted because we're actually, in most cases, under most conditions, you're going to get a cyclic concerted mechanism. Okay. It turns out if we look at these oxygens, this last oxygen is actually electrophilic. So first thing that happens is the nucleophilic alkene reacts with that electrophile. Now that does have lone pairs. These electrons go around in a circle. So the electrons attaching that oxygen to the other oxygen go towards the carbonyl. Then the electrons in the carbonyl go out to pick up the proton. These electrons come back to the oxygen. And it's actually this lone pair that attacks the carbon. So we have this kind of cyclic movement of electrons in the peroxy acid. And the result is that we've now added, in a concerted mechanism, the oxygen to the double bond. Right, plus we get the acid as a byproduct. Now, epoxides are stable molecules. You can put them in a bottle. You can buy them at the store in a tube of that epoxide glue. One of the tubes contains an epoxide, the other contains an amine compound, right? So they're stable enough to store and to sell and so forth, but it doesn't take much to pop open that ring, right? So the next step is going to be any questions about epoxidation. Okay. So there's three mechanisms that you see a similar kind of nucleophile attacking an electrophilic position, and then the lone pair of that position coming back and attacking the original carbocation, or what would have been the carbocation. That is oxymercuration, demercuration, right? First step with a mercury. The bromination or iodinization, right? So halogenation, and then the epoxidation. Well, all three of those have very similar mechanisms. Your alkene nucleophile is attacking something that's electrophilic, and then the lone pair of that electrophile in some fashion is coming back and attacking to make a cyclic ring. So we get a cyclic with oxymercuration, demercuration, cyclic with halogenation, and a cyclic with epoxidation, right? So when you're studying the mechanisms of these, put those three classes together. It'll help you understand what's going on and remember those three. If you forget mercuration, if you remember that mercuration is like bromination, then you can use that to key in your interest. Okay, so the first step is the epoxidation, right? We can use several different peroxy acids to do this. The second step is ring opening. And we're going to come back to ring opening when we get to epoxide reactions later. At this point, really what we're going to focus on is just acid catalyzed ring opening. So lone pair attacks the proton, electrons go over. We form this protonated oxygen, protonated epoxide. Then the water comes in, attacks from the backside. Okay, think about SN2. That puts the water down, the OH up. and that results in the dihydroxyl anti-addition. So first step is epoxidation. Second step is ring opening, right? When we get to epoxidation reactions with alcohols and thiols, we'll look at acid and base ring opening. There's a slight difference in the two, but whenever you're doing dehydroxylation, you almost always do acid-based ring openings. So the way you would see this is not as two totally separate reactions like that, but you would see it over one area. So let's say we use MCPBA, and it's the PBA you need to recognize, followed by then water and sulfuric acid. And let's put aqueous there. Okay. Questions about this one? So if we look at syn dihydroxylation, what we're going to use is a metal oxide. So potassium permanganate works well, and osmium tetroxide works well. You don't need to know the specific mechanism for this, but it is important to understand why it is syn addition, and that's because the intermediate here is this planar intermediate. And since that's a planar intermediate, both of those oxygens have to come down from the same side, right? So we're adding both oxygens to the alkene from the same side. So that gives us syn addition. Because of the formation of the manganese oxide and the osmium tetroxide, since that's a planar group coming in, you're not going to get alcohol adding for the bottom and the top. They're always going to be adding from the same side. Sometimes you'll see a two-step osmium tetroxide. What you're doing in that case is using osmium tetroxide as the catalyst, and you're adding another oxidant. The reason you do that is the osmium is toxic, and so. But if you see osmium tetroxide and you don't see pyridine, if you see something like NMO, what's happening is that you're still osmium tetroxide is your main reagent, but once you've reacted, right, the osmium tetroxide is not the osmium tetroxide anymore. And then you're oxidizing it back up with the NMO. So when you're looking through some of these problems, and if you're looking through other resources online, you might see NMO and you might see the catalytic version of the osmium tetroxide reaction. The thing to recognize is that osmium tetroxide, anytime you see it with an alkene, is going to give you a syn dihydroxylation. Okay, The manganese is not toxic. It's a little less easy to work with in the lab, but since y'all aren't in a lab, the potassium permanganate works perfectly fine. Okay, any questions about these? Right, so we've got two formations, anti and syn. Anti is epoxidation followed by ring opening. That's shown by some type of peroxy acid followed by water and acid. Syn dehydroxylation is going to be either the potassium permanganate or some type of osmium tetraoxide reaction. And we are going through lots of reactions today. I wanted to get through as many as we could so you can be working on the homework. Okay, so ozonolysis. Okay, so for ozonolysis, okay, first thing we do is add ozone, and then we're going to add a second step. We can add a reductive workup, or we can add an oxidative workup. In most cases, the reductive workup is the one you're going to see. In some of the older texts, they show the oxidative workup. We don't do that as much anymore, mainly because it gives you difficult products to work with. What's happening here is that we're going through and forming, and I'm not going to show the mechanism. You're forming this ozonide. Now, what do you notice in the ozonide, or what should you notice in the ozonide? We've already broken those two carbons, right? Those two carbons are no longer attached to each other. If we follow this with the reductive workup, then what we end up with is adding a carbonyl, an aldehyde, let's say aldehyde, to both of those two positions. So you won't need to know the mechanism for this one, but you do need to know that it goes through an ozonide. If we look up here, that's a little bit confusing, but in ozonolysis, one way to think about it is just okay, here we're just using the disulfide. When you see the ozone, realize you're going to be breaking that double bond. So you've got that side, add an oxygen, and you've got this side, add an oxygen, and right, that hydrogen was already there, I just didn't show it. So let's try one of those. So see the ozonolysis, we're just going to break that double bond. Okay. We could simply draw it this way, just kind of expand that out, or we could turn that into, right, 1, 2, 3, 4, 5. Turn it into the acyclic, or draw it out as a zigzag formation. It's important here to count your carbons. This is where students usually make a mistake. I'll take a 6-member ring and you'll do the ozonolysis, and the carbonyls will only be 5 carbons away. Right? Okay, questions about this? You can also turn alkenes into alkanes by reacting with hydrogen and palladium, platinum, or nickel. This palladium is just over carbon, so that just palladium is quite expensive. So what we do is we take small amounts of palladium, usually 20 to 30%, 25 is pretty standard, and put it on carbon, so graphic carbon, and that allows us to weigh it out a little easier. This is a syn addition. So if we think about our metal surface, and this is a heterogeneous reaction, we have our double bond. The double bond interacts with that. We also have hydrogen absorbed to the surface. So hydrogen will absorb to palladium, platinum, and nickel. We get then the addition of the hydrogen. So more or less the palladium interaction is weakening that bond, and then we form now the bond with the carbon, so the carbon-hydrogen bond, which is a much stronger bond, and then that floats off and another one comes in. So the palladium is just a catalyst. So that means if I take a substituted group, right, I'm going to get a syn addition. questions about that one? Again, don't need to know mechanism on this one. You need to know why it's syn addition. Both the hydrogen are coming from the same side since the alkene absorbs to the metal surface, similar to the osmium tetroxide and the magnesium oxide. They're both oxygens are coming from the same side, giving us syn addition. Okay, so let's look at what we covered today. We got oxymercuration, demercuration. Okay, that also embodies the hydroperoxidation oxidation. For anti-Markovnikov, we have the acid addition that we did last Thursday to give us alcohols, but with potential stereoisomer changes. We have halogenation, right? That's going to be an anti-addition. If we do that with water, we get a halohydrin. Again, anti-addition. Regioselectivity is Markovnikov's, the alcohol we add to the side that's most substituted. Dihydroxylation, we have anti and syn. Anti is epoxidation followed by ring opening. Syn, dihydroxylation, is with potassium permanganate or osmium tetroxide. No mechanism necessary, but it is important to understand why it attacks to the same side. Ozonolysis, we're adding ozone followed by a reductive workup. The ozone makes an ozonide. Then we reductively cleave that to give us our products. Okay, and then reduction of alkenes. Okay, this with last Thursday is all of our reactions of alkenes. So let's do a little bit of practice and we're going to look at the first few reactions in alkynes. So I'll put down a few reagents. You give me the products. Okay, so let's take a little time. Okay, on the first one, we can work through the first one thinking about nucleophile electrophile. So the alkene is the nucleophilic, the hydrogen is going to be electrophilic, bromine is going to be a leaving group. So the first step, we form the carbocation. Right. Second step, the bromide comes in and reacts with that carbocation. So I can work through the mechanism to determine, right, that I'm adding this. Of course, I could have just shown it is that, right? So without the mechanism, I don't have to worry about the hydrogen. So I can just show the bromine. So this is hydrohalogenation. We're adding a hydrogen and a bromine across. The second one, we're doing the oxymercuration demercuration. We could work this through with the mechanism. We also could learn, right, that oxymercuration demercuration gives us Markovnikov style alcohols. That means adding to the most stable side without rearrangement. So we'll add to the secondary position over the primary position. The third, we're getting osmium tetraoxide. So this one we don't really have a mechanism for, but osmium tetraoxide is going to form a syn dihydroxylation. So therefore, if I show this, right, that's the product. So some of these you'll have the mechanisms to be able to work through. Others you'll need to learn the reagents and what those reagents do. And again, the secret to remembering what osmium tetraoxide does, or the stereochemistry of tetraoxide, is thinking about that planar intermediate where you have both the oxygens attached at the same side. Okay, let's try another set. This time I'll give you the product, you give me the reagents necessary. Okay, let's take a look. So in this case, what we want to do is look at our starting material. Of course, that's an alkene, and our product. So here we have an anti-diol, right? So we have dihydroxylation. Since we're going anti, we're going to be using the epoxidation. Right, and we have several reagents for that, but really all we need is a CO3H. The R group on the side here is less significant. Then we're going to ring open that with catalytic acid, right? So water and acid to give me the anti-diol. This is one that I could work through the mechanism. But again, it's you're going to have to work through the flashcards to start to recall some of these reagents. The second one, if we notice we're actually changing our carbon skeleton, okay. Right now, you only know a few ways to change a carbon skeleton, so it's important to notice if a carbon skeleton is changed. One is carbocation rearrangement. So any of the processes where you go through a carbocation rearrangement, you can rearrange the carbons, right? But if you lose a carbon, there's really only one way now to do that, and that is ozonolysis. So first step, ozone. Second step, a reductive process. So we could use the dimethyl sulfide or the zinc and acid. What happens is I'm cleaving that double bond there, adding an oxygen both sides. I haven't shown the other product, but the other product actually turns out to be CO2. And what happens to CO2? It floats off into space, right? Well, not space, the atmosphere. The last one, I'm making an alcohol, right? And what type of alcohol? What do we know about the stereochemistry or the regioselectivity? This is added to the least substituted position, right? That is an anti-Markovnikov type addition. So if it's an anti-Markovnikov alcohol, that means I'm not doing acid catalyzed, I'm not doing oxymercuration, demercuration. I'm going to do hydroboration, oxidation. And since the boron and the hydrogen both add to the same side, that's why I show the addition I have here. So if we think about it, this hydrogen and the boron would have both been added to the same side, which means that that alcohol is inserted between the carbon-boron bond, so it retains that stereochemistry. So I've added the boron and the hydrogen to the same side. All right, questions about these? So the homework has a lot of practice. We'll do some more practice next week. I do want to get through all the reactions, and then we can do more practice and utilization of those. So I'm gonna go ahead and show the reductions of alkynes. That's the last part we have, is the alkyne reactions. In most cases, they're gonna mimic the alkene reactions, right? The only difference between, there's several differences, but one of the differences between an alkene and an alkyne is that an alkyne has two double bonds. So it actually has two pi systems to react with, where an alkene only has one. Okay. If we do a reduction of an alkyne, which is hydrogen palladium, this is the same reagent that we use for alkene, it'll go all the way to the alkane. Now you could say, what would happen if we ended up with one equivalent? So we measured out really carefully, and we put one equivalent hydrogen in there. What I end up with is a mixture of the alkane and the alkyne. That's because the intermediate here, better show it correctly, is that the alkene reacts with hydrogen and palladium faster than the alkyne. All right, so if I only try and use one equivalent of hydrogen, what happens is, as soon as I convert one of the alkynes into an alkene, it then reacts with the another hydrogen to go all the way to the alkane. So what I end up doing, if I try to use only one equivalent of hydrogen, and palladium and carbon is I end up with fully reduced alkyne to the alkane and unreacted. So therefore, it's not an effective way to stop. So there's no way to stop catalytic hydrogenation with palladium and carbon or platinum or nickel. So if I want to stop halfway, right, if I want to go from the alkyne to the alkene, I'm going to need special reagents, right? I'm going to need a special way to do that. And if we think about it, there's two possibilities. I could end up giving me the syn addition, right, which ends up with the cis, or I could end up with the anti-addition, which gives me the trans. Now the cis would be really nice if we could use the catalytic hydrogenation, right? But the problem is that the second step goes faster than the first step. So what I need to do is find a catalyst that'll go slower with this alkene or not react with the alkene at all, but will react with the alkyne. So therefore, what we use for this is we use a poison catalyst. Lindlar's catalyst, I think, is, if I remember, is I put palladium on calcium carbonate with lead carbonate and I believe pyridine or some other amine. Lindlar's catalyst is the way you usually see it. Usually when you see, if you're looking at other texts or other problems and you see some type of lead or nickel with a lot of other reagents, especially a lead-based reagent, that's going to signify a poison catalyst. So there's different formulations of these poison catalysts. Lindlar's catalyst is a standard one. You can buy it as Lindlar's catalyst. Is always the combination is already made up. But if you see a palladium or a nickel or sometimes platinum with a salt and then a lead salt of the same type, that's going to suggest that you have a poison catalyst. Okay. So Lindlar's catalyst, it'll be the one I'm using. But when you go and look out there at other resources online, notice if you've got some type of lead salt included. If you have a lead salt included, what they're doing is that's a poison catalyst. And what the poison catalyst does is allow the reaction to stop at the alkene. And it's a syn addition, both hydrogens add to the same side. Same reason that we saw syn addition with the alkene, right? The hydrogens are going to be absorbed to the metal surface. The alkyne is going to come down to the metal surface, and then the hydrogens are going to go up. It's just that when I poison the catalyst, I make the alkyne reactive and the alkene unreactive. So it's not reactive alkene, I can stop there. For anti-addition or the trans product, I need to be thinking about something that's going to be able to add hydrogens to both sides. And I do that by doing a sodium in amine. This is called the dissolving or dissolved metal catalyst reaction. Because the sodium is actually dissolved, and that gives me the trans. Okay, this one is actually a radical-based reaction. And we'll look more at that next Thursday. So the metal catalyst is absorption of the alkyne or alkene to the metal surface, When we go to sodium dissolving metal, the sodium and ammonia, that one is more of a radical type process. And we'll look at that next week, okay? So we covered a lot of reactions. Go home, make your flashcards, start practicing this. You should have most of the reactions you need to do most of the all of the alkene problems on your homework. I'll put some homework up for alkynes, and you should also be able to study those as well. Okay, we'll see y'all next Thursday. Remember, Tuesday is election day.